I'm Mark Gates, and we'll be talking about the SLATE library and MAGMA and heFFTe libraries. So Daniel and Sebastian will start off talking about the SLATE library, and then Stan will they'll talk about that for about the first half, and then Stan will talk about the MAGMA and heFFTe libraries for the second half of the tutorial. So go ahead, Daniel.
Perfect. So good afternoon. We're here to give the tutorial now on SLATE, so the basics within SLATE. Here we see the current up-to-date contributors of the SLATE library, and then at the bottom we have links to the slides if you want them for later or to follow along, as well as in the Bitbucket link to the examples for what we are going to show today. So the SLATE design it's the modern C++ replacement for ScaLAPACK, but the difference is we're templated off precision. So we provide the backwards compatibility layer to ScaLAPACK so that for applications that require or use the ScaLAPACK, that they can just transition to SLATE without any issues. But SLATE in itself is flexible. It allows for non-uniform block sizes and arbitrary distributions, although our default is a 2D block cyclic. The standards that we use is MPI for distributed communication, OpenMP for shared memory parallelism, as well as the key addition to SLATE from ScaLAPACK is that we provide GPU support. And this was developed from scratch as an ECP project. So this is our stack. We see SLATE relies on MPI, OpenMP, and so on, but as well BLAS++ and SLAPACK++. So these two libraries are actually libraries that we develop and maintain ourselves and are independent of SLATE. So if you want BLAS++ with GPU support, you can just use that library without needing to use SLATE. So just keep that in mind. But if there's something missing in this library as well, you can reach out to us and we can get that added for you. This is the varying SLATE coverage compared to ScaLAPACK. So we have the varying parallel BLAS. We do linear systems, least squares, SVD, and eigenvalues. So most everything that SLATE has, we also include, and we also include some additional things. So one thing that is forthcoming, so if you look in the SVD eigenvalue section, the vectors are still for SVD, down the line coming, but symmetric, generalized, and divide and conquer, those are implemented and should be merged within this year. So the outline for this talk is I'm going to talk about BLAS++ and SLAPACK++. Then I'm going to transition and give Sebastian control to talk about the creating and accessing these different SLATE matrices. Then I'll come back and talk about the different routines and things that we have within SLATE and how to use them. And then we'll end with the different platforms and availability of SLATE. Within BLAS++, the previous BLAS operations, you would need to specify what type of precision you wanted to do your operation. So if you wanted to call norm, you would have to specify single, double by appending that letter in front. Well, what we've done is remove that complexity and created a wrapper around the precision. So all you need to do is call norm, and then based off of the type of the object you input with, we will call the correct precision BLAS routine. Additionally, we've added enums. So instead of the traditional BLAS implementation where you would do L for left, L for lower, or T for trans, we are explicit so the user can see and immediately know what's going on. So we say BLAS side, we want left. BLAS up low for upper lower, we want lower. So that's as well as we should note that SLAPACK++ only supports column major, whereas BLAS++ supports both column and row major with very minimal overhead. So BLAS++ also now provides GPU support. So the difference here is, well, if we have a device, then we have to create this queue. So we call BLAS queue, which is a queue and gives the ID of some device as well as a batch size. And then when you call some routine like gem, you just need to call the traditional parameters appending with a queue at the end. And then after the call, you just need to sync so that we know it's been happened. So simplifying those name changes by removing the types of precision actually is a little confusing in the sense that there are differences between real and complex. So circ refers to a real matrix operation, whereas if you were dealing with a complex, it would be HERC. What we've done is we've assumed the complex version for all. So since complex always implies real, but real doesn't always imply complex, we've decided to go with this transition. So if you call HERC, but the matrix on input is real, really what we're going to call is circ. But there is the compatibility to go backwards. So sometimes you have a complex matrix, but you want to do the symmetric operation instead of a HERC operation. So if you call BLAS circ with a complex object, then we will do the corresponding C circ, Z circ. So some applications do require this. So the differences with BLAS++ and SLAPACK++, or I guess not differences, but some additional information, is that SLAPACK++ allocates all the workspaces themselves, as well as we throw hard errors. So like if the leading dimension is less than m, the number of rows, we throw a hard error and exit. But in addition, we throw the numerical errors that traditionally SLAPACK would throw. So it returns an info. If it's larger than 0, then we know that either there's a NaN introduced or a singular matrix is fed into the routine, but we won't exit right away. You'll just get this at the end. Additionally, we use int64t for all our integer arguments. So if a vendor provides 32-bit int, we convert that to int64, and so to avoid those overflows. BLAS++ and SLAPACK++ provide coverage on CPU and GPU. So level 1 BLAS and level 2, there's some that are on GPU, but mostly we focus on CPU for those. If there are something that you would find useful and want access to on a GPU, please just let us know and we can get that added. But we focus mostly on the level 3 BLAS because that's where we get most of our performance increase, as well as we provide all these different batched BLAS operations. So most functions of interest in SLAPACK we have on CPU for SLAPACK++, but now we've actually transitioned to starting adding some GPU support. So like POTRF, GTRF, GQRF. So if there's something that you would find useful and want to use on GPU, please let us know and we can get that added. So the different types within BLAS++, you can use real type, complex type, or scalar type. So if you use real type on some object, it would strip away the complex values. If you use the complex, it would add the complex values back. Well, not back, but it would add that aspect to the type. Otherwise, we do provide this BLAS : scalar type, where if you are comparing two objects, it would take the simplest type to represent. So if you had scalar type of float double, then it would convert both to double instead of looking at float and double, because it allows the comparison. It allows it to represent in the simplest type. So here's the tree for that. Float double would go to double, float complex float would go to complex float, and so on. So two utilities specific that I feel we need to mention is we never use std conj. We use BLAS : conj instead. And the reason that we don't use the standard is the standard conj always returns complex, even for real input. And sometimes we need a real on output. So what we've done is we have BLAS conj that takes in a complex, outputs with a complex, takes in a real, and outputs with a real. So this code down here is just it'll show you the example of the difference between STD and BLAS using the conjugate. As well as, so we use BLAS min and BLAS max. So if we use the STD max, let's say we have an arbitrary number of items and each of these items have an arbitrary type. Well, if you use the standard max, you may not compile because it can't distinguish between an int64t and an int, whereas BLAS max would, and it can distinguish between these types that are cast sensibly. So, and now I'll give this to Sebastian.
Thank you, Daniel. Okay, so now we're going to talk about the matrices in SLATE, how we can create them, how can we access the data, and so on. So let's start if it works correctly. Yes. So what is the matrix in SLATE? Matrix in SLATE is just a collection of tiles. and we are using an STD map to access them efficiently. So what we have is we have a tile ij, is row, js column. It could be located, bless you, or on the device. So we just create a tuple ij and device index, and we can manage our tiles. This allows us to have a global addressing of the tiles. And this is very helpful when you have a distributed matrix. On top of that, we can manage the GPU. We can manage the data, movement, the tile, the memory, and everything. On top of that, it's very helpful because we can avoid wasting memory, especially for symmetric or triangular matrices. Also, is the case for band or block sparse matrices. So on the bottom here, you have an example. On the far left, you have a general matrix. The tiles could be square or rectangulars. The next one is a lower triangular matrix. Here, all the white tiles correspond to non-allocated piece of memory. So we are saving memory. The next one is a band matrix. Again, all the white tiles correspond to the saving we can have by using tile approach. And the last one is a lower band, lower band matrix. So this is great, but this is very also helpful because we would like to be backward compatible with LAPACK and ScaLAPACK. So let's look at what is a tile. We want to be able to use ScaLAPACK format or our current tile format. So let's start with the ScaLAPACK format. In ScaLAPACK, it's a 2D block cyclic, as Daniel said. The idea is you allocate one big chunk of memory. You have your local M, and you have your local leading dimension. And in this, you can create tiles. So you just cut it into pieces, and you're fine. On the other side, you can have tiles that you allocate individually. So here you have 9 tiles, where for each tile, the memory is contiguous. And you have number of rows, NB, and number of columns, NB. Those have advantages. For example, one advantage for the right approach is that when you want to send a tile, the memory is contiguous. So you're going to do one send and you don't need to unpack your data. So it's good. Then you have your matrix. It should be, or we want it to be distributed to be efficient. So let's consider a 2x2 grid. We have our global matrix A, and we're going to distribute it in a column major way, which means let's consider the first 2x2 tiles on the top left corner. We start by numbering from the first column 0, 1, then we move on to the next column 2, 3, and we repeat this pattern. So the good thing with the tile is that for each rank, they just need to insert the tile corresponding to their rank to the distribution. So they all have 4 tiles. We're using a map, so everything else is not allocated. And now if, let's say, rank 0 wants to send the first block column, what he does is he's going to do the communication, but beforehand, all the other ranks will just insert the corresponding tile, and then they will receive the data. Again, this works for both ScaLAPACK or the individual tiles, which is great. So now let's move on to the examples. So a first simple example, example 1 that you can find on the repo. Here we are creating a matrix of size 2000 by 1000 on a 2x2 grid. So first we include the SLATE header file, and we're just looking at the main function. As Daniel said, we rely on OpenMP tasks, so we're going to have a lot of threads. So we need to have an MPI that allows us to have a thread that will initialize a communication. So for that, we do MPI init thread, and we're using the flag MPI thread multiple. And then we create our matrix. So we're going to do SLATE column matrix. We're giving the data type. Here it's double, and we have our matrix A. And the parameters we have to give is the number of rows, 2000, number of columns, 1000, NB, which is the block size, which is the size of the tile. It's going to be 256 by 256, and then the grid size, P and Q. And finally, what we're giving is a communicator. So when we do that, we have all the metadata we need. We can build the distribution and everything, but we do not allocate anything yet. To do that, we're going to call this routine. So we're going to do a.insert local tiles. This will manage the memory for you and insert the tiles. So we have the tiles locally, and now what we want to do is put some content in it. So we're going to have two for loop. We're going to go through the block columns and the block rows. And what we're going to do is we're going to do an if statement. If the tile ij is local, we have the memory and we are able to set it. So what we're going to do is we're going to create a temporary tile, just a metadata, so it's not an actual copy. We're going to do slate colon tile. We're giving again the data type, and it's going to be t that represents a parenthesis ij. And then we can fill in this tile by calling any routine like random matrix, where we give the number of rows using MB, number of columns, using NB, the pointer to the memory, and the stride of the LDA. And we're good. So we have a memory that is allocated, and at the end of the day, we call MPI-finalize. So if we want to compile this, very simple as usual, you provide the path to the SLATE header files for the compilation, and during the linking phase, you just provide the SLATE library. And at the end of this slide, you can see a simple example. You do MPI run -NB4 and your executable, and it's going to work. So this is the, let's say, the default approach. Now we want to be backward compatible. So what we're going to do is also provide a routine for ScaLAPACK. So it's slightly different. Here, when you create your matrix, you're going to call the from ScaLAPACK routine. And the only difference between this one and the previous routine is that you have two additional parameters, data and LLD. So data is the pointer to the memory you want to use that you allocated beforehand, and LLD is the local leading dimension. All the other parameters are the same. Now keep in mind that since you're providing the memory, you are responsible for it. You need to free it when needed. SLATE won't do it for you. User retain ownership of the data. This is really important. So no matter what, you're creating your matrix. So actually, you're creating an empty matrix by calling the first snippet you can see here. And then, as we showed you before, we're going to insert the tiles locally by calling the insert local tiles routine. Actually, underneath, what happens is you have a double for loop. We have this if statement, and if the tile ij is local to your rank, you're going to insert it. So you're going to do a.tileinsert ij. By default, it's going to be on the host, so the CPU. We also introduce flexibility to do it on the GPU, on a device. So here you're going to add additional parameters. In the first case, it's just adding target colon devices. And for the equivalent snippet, it's going to be at the end when you do tile insert to add the third parameter, which is a.tileDevice ij. And it will be allocated following the distribution to the corresponding device. Similar to ScaLAPACK, the user can provide its own memory space. So to do that, when you do the tile insert, we have two more parameters. So we have ij, and now we have data ij, any pointer you want, and the local leading dimension. Again, same remark as ScaLAPACK, the owner retains ownership of the data. So this is very flexible, but you should avoid memory leak. So we are able to create a matrix. We are able to allocate the memory or get somehow a memory space. Now we want to play with it. We want to access the data. So first of all, let's look at the matrix. So we have a matrix A, and if we want to get the number of block row or block column, we have two routines, a.mt or a.nt. So with that, you can iterate over the tiles. And if you want to get 1, you're going to do like t equal a parenthesis ij. That will give you the tile ij on the CPU. You can also do the same on the device, any device, by adding an extra parameter, which is the device ID. If you do that, you're getting the memory on this specific device. Now you have a tile. That is good. We have the same routine if you want to play with the data that are inside the tile. So we have t.mb and t.nb to get the number of rows and columns of the tile. And then if you want to access one entry, let's say iijj, you're going to do t parentheses iijj. You can also do t.at iijj. The only difference between those two is that the second one, you're not getting the conjugate of the value. So this is something to know. Okay, so here is a very simple example. It's a toy example. So we're going to have our 2 for loops to iterate over the block columns and block rows. And then if the tile ij is local to the rank, we're going to get a kind of a label. So we're going to do auto t equal a parenthesis ij. And then we're going to iterate to access to all elements of this tile by saying t.at iijj equals something. Keep in mind that it's not very efficient to call t.at at the most inner loop. Again, it's a toy example just to show you how you can play with those functions and quantities, how it works. Okay, so we are able to create a matrix. We're able to put some content in it. But in SLATE, we have different matrices, and we can benefit from the property of those matrices. So what we did is we created a base matrix. This is a default value. And on top of that, you can generate or create a general matrix. It's going to rely on base matrix because base matrix will contain all the standard value, number of rows, number of columns, the block size, the grid dimension, and so on. So you can create your general matrix, but you can create also a base trapezoidal matrix. The difference is one additional parameter. So here is going to be, is it upper or lower? And from that, you can create a trapezoidal matrix. Again, from that, you can create even a triangular matrix by adding an additional parameter, which is the state of the diagonal elements. Is it unit or non-unit? And you can do other stuff like symmetric matrix, Hermitian matrix. Here, the idea is which part is the symmetric, the opposite of the other one. We extended that with band matrices. So again, we start from the base matrix, and we're creating the base band matrix just by adding one parameter, which is the bandwidth information. And from that, you can get a band matrix. You can play with that by adding more again, so you can get the base triangular matrix that gives you triangular band matrix or Hermitian band matrix, and so on. Keep in mind that for now, we need to explicitly zero out some tiles. It can be improved, but for now, this is the current state when you're on the band. Also, it's relatively new. So we're still developing, adding new features. So expect more development. And if you want to give us your feedback, you're more than welcome. So we have a lot of matrix types. We have the second example in the repo is about the conversion. So you have your matrix, but you want to play with that. So let's say you have a square matrix A of size n, and you want to extract the triangle, the lower triangular part, L. So you're going to do SLATE colon triangular matrix of type double L. And here you just need to provide if it's upper or lower. In that case, it's lower, and the diagonal is unit. And you get all the remaining information from A. You can do the same for the upper triangular part of A. You can even create a symmetric matrix, S, from A by saying, I'm just considering the upper triangular part. So now one may ask, okay, but is it costly? Because here you have A, it may take some time to do it. Then you're getting L, U, or S. And actually, the answer is no, because here everything is about metadata. So we're talking about shallow copy. So let's look at what it is with more info. A shallow copy, remember, a matrix is just a map of tiles. Those tiles will be using shared pointers to point to the actual memory, but the matrix is just a map. So let's say we look at the bottom left corner, we have a matrix A. We have its map, the representation, the memory, and everything. Now we want to consider the trailing matrix, which is the last 2 rows and the last 4 columns. So we can get a matrix B, calling a routine that we will discuss later, which is sub, and we're getting the trailing matrix B. Now let's say we want to use the transpose of B, and now it's going to be C. So we have A, B, and C living at the same time. But there is no actual copy, no data movement. Everything is pointing to the same matrix storage. And that's why it's good. So that's great. We have lightweight operation. And we're going to operate on shallow copy of matrix or tile. So what does that mean? If we look at like the transpose we just showed before, we have a matrix A, and we can create AT, which is a transpose of A. AT is just a shallow copy of A, where the flag up is now equal to transpose. And if we look at the tile ij of the matrix AT, it is the transpose of the tile ji of the matrix A. We have the same with the conjugate transpose. We can create the matrix AH, which is a conjugate transpose of A. And now AH is also a shallow copy of A, where the up flag is conjugate transpose. And again, if you try to check, the tile ij of the matrix AH is the conjugate transpose of the tile ji of the A matrix. So when I showed you about the shallow copy, I was mentioning the subroutine. One very important feature is to be able to play with submatrices, like the trailing matrix, like the panel, like whatever. But it's really important to extract that. We just showed that it is possible to do it with a cheap cost. So now we're going to talk about how we can get submatrix, and we have an example. Example is 3 in the repo if you want to get more details. But basically how it works is based on the tile indices. So you're going to do a.sub of, and then you provide 4 parameters, I1, I2, J1, J2, that are relative to the rows and columns, which is in the MATLAB notation, completely equivalent of doing a parenthesis from row I1 to row I2, and column J1 to column J2. Keep in mind it's inclusive. So we can look at a few examples. If you want to get the first block row, what you're going to do is a.sub from block row 0 to block row 0, and from block column 0 to block column at the end, which is a.empty -1. We can have the same for the first block column, the first panel, let's say. And for that, we're going to do a.sub from 0 to the end, which is a.empty -1. And for the column, from 0 to 0. And we can obviously extract the trailing matrix by doing a.sub from 1 to the n, which is a.empty -1, and 1 to the n, which is a.empty -1. Again, everything is shallow copy, so almost no extra cost. We can go even further. We can slice the matrix. Everything before is based on the tile distribution and the indices of the tile. Here, what we can do is we can use the row and column indices instead of the tile indices. By doing that, we're just going to do a.slice row 1, row 2, column 1, column 2, which is in the MATLAB notation again, extracting the row and column, going from row 1 to row 2, and from column 1 to column 2. Again, it's inclusive. So if you want to get the first row, we're going to do a.slice from 0 to 0, for the rows, and from 0 to the end. Now here it's not a.nt, but a.n, because we're in the space of the columns, not in the space of the tiles. We can do the same for the first column. It's going to be a.slice from 0 to a.m minus 1, and for the column from 0 to 0. And we can even describe arbitrary region. It has to be contiguous, okay, but it's an arbitrary region. Here you say a.slice from I1 to I2 and J1 to J2, and you're getting this piece of memory. So keep in mind, obviously, it's going to be less efficient than just a sub because it involves some operation on the indices. But it's very helpful, very powerful. Also, one more thing, it's less supported. We have less algorithms that support this for now, especially on GPUs. But still, it's very helpful. So now I'm going, Daniel, you're taking the lead.
Yep. So back to me, we're going to talk about the varying SLATE routines that we have, and we'll begin with the norms and BLAS. So difference with the norms is we have this enum class to specify what type of norm you may want. So you have some arbitrary general matrix, and you can create a double of the norm value that you're going to get. And all you do is call norm of, and then you put that enum, norm colon colon, whatever type that you want, max, one, inf, fro. If you want the two norm, then you're going to have to compute the SVD of the matrix. But we also take advantage of these varying matrix types that Sebastian talked about. So if you have a symmetric matrix or a trapezoid matrix, we can reduce the number of flops done by avoiding those tiles that were never allocated. For matrix multiply, we have varying types in BLAS, gem, sim, hem, and instead you can call SLATE colon colon multiply. And this is a simplified API in the sense that you don't need to specify left or right for sim or hem. You can just immediately put the object in the location that you want. So for this first SLATE multiply, we have A on the left, so that implies we want it to be operated on the left. Whereas the second, we have it on the right, so we want to compute on the right. As in addition, so with these different gem, sim, hem, the SLATE multiply routine actually will figure out the type that you're getting under the hood and perform the correct operation. So it just simplifies your life a little bit easier. But the older routines, the original routines, gem, sim, are available for the user if that's their preference. We also provide rank K and 2K updates. So you have CIRC, CIR2K, HERC, HERC2K, and the simplified API would be rank K update or rank 2K update. So nothing's different in the parameters that we input with for these, other than you just have a simplified name for somebody that is not familiar with the routines. They wouldn't need to look up prior to implementation or reading the code to understand. We also provide triangular multiply and triangular solve, so a TRMM, a TRSM, and the difference is triangular multiply or triangular solve. And again, we provide the concept of positioning your input matrices as a left or right to take over the enum of BLAS side left or BLAS side right. So these transpose, the upper, lower unit, non-unit properties of the matrix are flags within themselves and not needed to be passed as parameters. As well as, I should point out, this is specific to example 5 in the example routine. So options is an additional thing that SLATE provides. So for one, we have this look ahead idea. So you can feed the number of look aheads that you want to see how much if you have any idle CPU, GPUs working, they can look ahead and do a little bit of pre-work to get better performance out of your routine. Similar to specific routines have additional parameters. So GQRF, the QR factorization, has this inner blocking parameter, IB, which you can tune to get better performance for your application. For linear systems, we have LU, Cholesky, and LDLT. So for LU specific, this one's example 6 in the directory. We have to create our slate matrix A, the number of right-hand sides B, as well as these pivots matrix. So the traditional way would you would either use GESV to do both, or GTRF then GTRS. And those are still available again for those that would prefer to use it. But we do provide this simplified API where you just say, I want to do an LU solve, and then you don't even need to worry about the pivots involved. That's under the hood taken care of because you have the solve factor being what's returned. But if you do want just the factor and then solve using the factor, those are available as well. For the Hermitian positive definite case, so as symmetric positive definite, we have Cholesky. So you have to create your Hermitian matrix and then the number of right-hand sides again. But the traditional implementation would be POSV or POTRF and POTRS. And what we've done is we've just simplified it again, saying we want a Cholesky solve. So Chol solve, Chol factor, Chol solve using factor. There's nothing different between the input for these two, but solely the fact that somebody might be able to read this and instantly know what's going on. For the indefinite case, the LDLT, we have a lot more parameters, things that's going on. So you need your Hermitian matrix, you need your right-hand sides, then you have these 2 workspaces, HT, as well as 2 extra pivots. So we have the HESV, which is the traditional call to do the factorization and then solve, or you can just call the indefinite solve and not need to allocate and worry about all these additional things. Everything is taken care of under the hood. You just need your Hermitian matrix as well as the right-hand sides that you're trying to solve with. A key thing with SLATE is we're providing the different precisions. So we want to develop more mixed precision algorithms. So for here, this example that I'm showing is mixed precision of a Cholesky factorization as well as a solve. So the idea is that we have this algorithm and we want to do the factorization, most of the work in single precision, because single precision can be twice as fast as double. But the issue is then our solution is in single, but we can do this iterative refinement to obtain double precision accuracy from the single precision factorization. And that's what these results are showing. So the blue lines is a full double precision factorization and double precision solve. The green line is single precision factorization, and then we do iterative refinement in the solve to return back to double precision accuracy. And as you can see, the double precision is kind of maxed out between 1500 and 2000 gigaflops. So I should say on the x-axis, we vary the matrix size. On the y-axis of the left plot, we're looking at the gigaflops per second. The y-axis on the right is the performance increase, the speed up from double to single. So as we increase the matrix size, we see continued performance increase from doing the work in single precision while obtaining similar results. So matrix inversion, that is something that we provide. So you would use traditionally GTRF, GTRI, or you can call LU factor and then LU inverse using the factor. So the caveat though is you should use LU solve or Chol solve for that because, well, for one, it's faster, and 2, it's more accurate. So we know that computing the inverse of matrix, it can be very ill conditioned. So, but it's available for those who absolutely need it. For the least squares problems, we have QR or LQ. So for QR, we're trying to solve overdetermined systems. So we start with a general matrix A, the number of right-hand sides, and the idea, the benefit to some of these structures within SLATE is we don't need to allocate space for B and X individually. Since X is existing within kind of like with B, we can take a slice of B and write X in that same memory so that we don't have to allocate additional workspace or objects. So the traditional way again would be to call SLATE gels or just gels, but we also provide the least squares solve. For an underdetermined system, so traditionally this would be LQ, similar idea. You just have to create your matrix, you slice B into X this time because it's the opposite dimensions for being underdetermined, and then you do your solve. So you call gels again or least squares solve. For SVD and eigenvalue problems, this is the last one that I'm going to talk about today. For SVD, so we use this two-stage reduction to bidiagonal. So first, we can take a general matrix A, compute the QR factorization, take that R factor that's produced, and reduce it to a banded matrix, upper triangular banded matrix. We reduce that again to a bidiagonal matrix, and then finally reduce it to the diagonal matrix with the singular values on the diagonal. So the singular vectors have not been implemented. The current, if you remember from the fourth slide, we state that it's coming in 2023. So sometime in the near future, but not there yet. GESVD would be the traditional call, whereas SVD vals will get you the singular values in SLATE. For the Hermitian case, we don't need to do QR. We can go straight to bands. So we take a general matrix and go to a banded matrix, then reduce the band to a tridiagonal, and then reduce the tridiagonal to diagonal and get those eigenvalues right away. And for this one, the eigenvectors have been implemented, but they're not merged into the master yet. So that's coming hopefully later this year within a few months. So whenever the next release is, we hope to have the eigenvectors added in. And then finally, we have the generalized Hermitian eigenvalue problem. So same as the eigenvalue problem, except now we introduce this Hermitian positive definite B matrix. And depending on where you want this generalized aspect to be included, this first line where B is on the right-hand side of the equation, or left side, but on the right of A, or fully on the left side of A, you specify these different types. So you would feed it into HEGV and get 1, 2, or 3, and then you would output with your eigenvalues. So the eigenvectors, again, here are forthcoming. And I am finished with all the routines, and we'll finish with the platforms and availability.
Okay, perfect. Thank you, Daniel. So in the last few minutes we have, we want to unphase one thing, if it's moving. Yes, okay. So SLATE started historically with a full implementation using CUDA. It was great, but not very portable. And since then, SLATE was refactored to use BLAS++ as a portability layer. So the idea is BLAS++ provide the support for all the architecture, and SLATE just query BLAS++, and it's gonna work. So BLAS++ for now is working with CUDA, so NVIDIA GPUs, AMD GPUs. For Intel, it's a work in progress. But that should be done soon. We also have some kernels in SLATE, some kernels that cannot be integrated into BLAS++, at least for now. So again, we have the CUDA version. We EPify them to get the heFFTe version, which is fine. But we're also working on porting some of those kernels using OpenMP offload or SQL to, again, support the 1MPI, 1MKL. So it's a work in progress, but so far, I would say 2/3 is well supported, and that should be completed eventually. And to finish, to conclude, the user guide can be found as well as the papers that we're writing when we are developing this at this URL, icl.utk.edu/SLATE. We're using Bitbucket for the repo, so we have 3 separated repos. As Daniel said, those are independent projects. It's more like SLATE needs something, so we may add something in BLAS++ or may not. So they are independent. So we have the SLATE BLAS++ and ScaLAPACK++. Overall, we're using issue tracking. So if you have any issue, please go on Bitbucket, raise an issue. Sorry?
Let's now make sure that you don't miss out on one.
Okay. So if you have any issue, please report it, and we're going to address it quickly. And we're using also pull requests. So if any user wants to contribute, please feel free to fork, do some changes, and create the pull request. And finally, We have a user forum, so if you have any questions or just want to discuss something, go on it and we will be happy to answer. That's all on our side.
Perfect.
So if you have any questions, I don't know if we do questions now or at the end of everything.
Well, I can stop sharing to let Stan take lead at least.
Also, in the meantime, if you want to write your questions on the chat, you're more than welcome.
Okay, so if there are no questions now,
so there's one question in the chat. Do you use Cocos to launch kernels on the GPU? No, right now we're so any kernels that we wrote ourselves are either in CUDA or HIP or eventually in OpenMP offloads. We're not using Cocos. Yeah, that might be an option in the future. Yeah, go ahead, Stan.
Okay, so I will continue with this second part, which would be a MAGMA tutorial and followed briefly by a heFFTe tutorial. These are libraries that are linear algebra libraries, part of Clover, and supported also from other ECP projects. Starting with the MAGMA tutorials, MAGMA has been developed over the years. These are some of the developers with star. We have marked here some collaborators that have moved to other places than ICL, but the library is basically developed at ICL and provides SLAPACK for GPUs. This is the outline for this tutorial. So we will start with introduction, and then availability, routines, code, testers, and methodology. Basically, the brief version is that MAGMA provides the SLAPACK for GPUs, so it's the single node functionalities that you just heard about SLATE that is providing those type of routines for GPUs. And this is a summary of the different routines that MAGMA provides. So it's a shared memory library for a single node, although it can use multiple GPUs if available. And it provides the SLAPACK and BLAS for GPUs. Most algorithms are hybrid to use both the CPUs and GPUs, but also has some new routines that all are not part of SLAPACK, namely the batched routines for linear algebra, and these are both BLAS and SLAPACK, and it has also a sparse linear algebra component. These main classes are briefly illustrated here. So for dense linear algebra, for example, we always target to get close to the peak of the machines. As you can see here in double precision, for example, LU, we get close to the peak. Still, what is interesting to note is that the lines are still growing up in with the matrix sizes. So typically for other architectures like CPUs, it would flatten pretty quickly, but for highly parallel systems, it's difficult to scale, but still when the data reuse gets high enough, the performance gets close to the peak. And we support the different architectures. So right here we provide and show the performance for NVIDIA GPUs. This is the A100 GPU on top. We have updated also for HIP. This is, for example, the MI250X performance on Crusher. And we do similar for the batch routines. This is what MAGMA is today. Mostly what we are concerned here is the support for CUDA and heap, and we have pretty full support over the different routines. We have about 2 releases per year. Number of downloads is about 4,000 per release, although the last few have picked up with significantly more. For example, the latest 2.6.2 has been downloaded 13,000 times so far. And MAGMA is used in many packages. Some are shown here. In ECP is also heavily used. These are some of the projects that need it, that we are aware of, and we collaborate with these people to incorporate MAGMA there. In particular, SEED, MAGMA is in the SEED Co-Design Center. This is for high-order finite element methods, mostly using the MAGMA batched functionalities. And it is part of the SEED software ecosystem. Dense linear algebra is used, of course, in many packages, even if it's nodal, as you can see here in this dependency chart created by ECP. Right after packages that everybody has to use, like SPAC for installation or for parallelism, OpenMP and MPI. Next in use comes SLAPACK and BLAS. So they have a lot of dependencies, and we don't track all of these, but MAGMA provides these routines, and also it provides optimized implementations for the new architectures. Some of the current work, we stress a lot on the mixed precision solvers. This is to harness certain hardware changes that have happened recently, both hardware enhancements for lower precision, as well as different data formats and instructions to do the computations. And I will show a graph in a second about that. Other current work that is getting incorporated now is batch linear algebra. For example, we are adding SVD, batched SVDs. Recently, we added variable size factorizations like LU and solvers around that. There are many performance optimizations for different architectures. We also have user requests and additions to the library. For example, inertial computation used in HIOP, LDLT factorizations, and things like that. Tensor contractions, as I mentioned, in SEED. Various data analytics kernels. These are CUDA and heap kernels. Included are also what we do for FFTs in the heFFTe project. And of course, porting to other programming models. We have already heap and CUDA ports, and Intel GPUs now is in the pipeline. As I mentioned, the mixed precision, you can see here some of the solvers and the acceleration that you can get using the low precision. And these are for V100, for the NVIDIA GPUs, V100 and A100, and for the MI100 and MI250X from AMD. So in all these cases, you can see that we can achieve under certain conditions FP64 accuracy, but much faster when we use these hardware accelerated features and formats that these architectures provide. So that's amazing performance. For example, looking here, let's see here for the A100, we get 55,000 gigaflops per second solving in FP64 accuracy. That's an amazing speed achieved just by a single GPU. And these make sure take into account the different hardware characteristics. Another improvement recently added is batched SVD performance. We typically compare with state-of-the-art libraries. In this case, is CUDA solver. So performance and of interest are very small sizes. We can see here the speed up on the right axis given by this curve. So for small sizes, the speed up that we achieve is about from 12 to 2 for larger problems. Another interesting routine that we just added is for variable size LU factorizations. These are used in packages like SuperLU for large sparse direct solvers. And again, we show here current performance results in terms of gigaflops per second. So higher is better of the new routine here in purple versus whatever else is available, like on the CPU or in this case, QSolver. So on the left is NVIDIA A100 versus on the right, we show results for the MI100 GPU from AMD. In both cases, as you can see, we get very good performance accelerating these type of routines. So MAGMA today has grown. There are around 3,000 routines per architecture, so ports become challenging just due to the volume. But still, we can pretty easily port to new architectures, as shown recently with the heap. So, and that's because we use standards. For example, everything is written in terms of BLAS for performance portability. There are various abstractions that keep the base code unchanged. And then we use a lot of translation tools to automate the process, coupled up with auto-tuning at the end. The latest release is 2.6.2. This was released March 15 this year. The main thing was the heap support and optimizations in heap. Now the CUDA and heap functionalities are in sync. MAGMA sparse is added and is supported for AMD GPUs. Of course, all the installations are supported as required in ECP, for example, including CMake and SPAC installations. And then there are a number of improvements and extensions, as I already mentioned some. So moving to the more standard tutorial part of the presentation. So availability, MAGMA is available at ICL MAGMA homepage or Bitbucket where the repository is. The support is for CUDA and heap, which are of interest now. And on many systems, it may be already installed. So it's worth to check, for example, if MAGMA is there for users. Other than that, if it has to be installed, we support makefile installation, very similar to SLAPACK, where a user can edit a make.inc file to adjust what compilers and flags are to be used. And then you install it just like that. Or typical CMake installation and adjustments. And SPAC, if everything works, again, can be installed just like that, or adding other specifications. Moving to routines, so these are the standard routines in SLAPACK plus BLAS routines, and then most are hybrid SLAPACK style functions. For the BLAS, we have most of the BLAS covered and auxiliary functions. And then there are also wrappers around CUDA and QBLAS and ROC-BLAS to always get the highest performance. So routines that are, for example, called MAGMA DGEM, these could be wrappers calling the underlying vendor implementation or MAGMA. This is the naming convention. The routines are prefixed with MAGMA underscore to indicate that it's MAGMA. After that is the name of the routine, following exactly the SLAPACK style. So in this case, the first character is for precision, Z for double complex, and so on, as described here. And then you have mixed precision routines, followed by the matrix type. So it could be general for general matrices, orthogonal, or all these listed here. Then followed up by the functionality of the routine, SV, for example, for solvers, or TRF, triangular factorizations, and so on. After that, you may have a suffix underscore GPU. This would indicate that the matrices passed to the routine are on the GPU memory, and the result would be on the GPU. If there is no underscore GPU, standard SLAPACK format is assumed. So matrices are as if they would be used in SLAPACK, is just underneath the GPUs would be used to accelerate the computation. More specifics on the routines provided. So these are the linear solvers. So these are the routines from SLAPACK. As you can see, these are almost all supported. We have mixed precision also for different matrix types. We are adding now also banded matrices. These are for the eigenvalues and singular value decomposition for different matrix types, different types of operations, and how the routines are named, along with the supported interfaces. These are computational routines, also all supported. So for different matrix types, the operations, LU, solve, inverse, for symmetric and positive, Cholesky, and for QR type of factorizations. These are the BLAS and auxiliary routines, level 1, level 2, and level 3 BLAS, again following the BLAS convention, and many auxiliary routines as well. Okay, moving to the matrix layout. So layout is standard SLAPACK layout. You have a leading dimension, and then up in that box, you can specify submatrices for which one would like to do some SLAPACK type of computation. So it's column major layout like this. And then you have special matrices like symmetric or triangular, and the storage is as illustrated here. And we have also banded being added right now. These are just some simple examples of the usage. So if we want to solve AX equal B, the code would look like this to solve it with SLAPACK. And the same, if we want to use magma, the lines in red indicate the changes. So one would include the magma header, there would be a magma init, and then DGESV would just be replaced by magma underscore DGESV. And then there would be magma finalize at the end. So it could be as simple as that to port your code to GPUs. This example illustrates the GPU interface where the pointers are on the GPU memory. So one may want to allocate memory on the GPU unless it's already allocated. And then those matrices would be filled up in some way. And then the corresponding routine would just add underscore GPU to solve that. And the solution would be on the GPU memory. Again, they're memory free at the end if needed. This is a simple example how to multiply matrices. So this is the DGEM. These are asynchronous methods. So a queue is created and the computation would be passed through that queue. So after the queue is created and there are matrices initialized in some way, one can call magma DGEM and pass this queue. This would be a synchronous execution in the sense that control would pass to the next command, and the user may request other computation to go in parallel in another queue, or if this result is needed for something, it can be pipelined in this queue, the computation, or just make sure that it's synchronized like this. That's a way for DGEM to finish magma queue sync. And as you can see here, there is no mention of the architecture. So most of these codes, they have syntax that does not depend on CUDA or heap. So that's the nice thing about porting also easily magma, because many of the codes are written using magma wrappers, even for the BLAS functions. Next, there are some examples about different types of copying data around that magma supports. So there is set, get matrix, to the device and from the device. It could be for vectors. Default is synchronous, so this would copy synchronously. For example, this set matrix would set this matrix A to the GPU. Corresponding is dget matrix. And then there are asynchronous copies, just as illustrated here. The memory allocation to use those has to be pinned memory. Magma provide wrappers how to handle those routines. One can use directly CUDA or heap, but then again, one would have to maintain code for all those different programming environments. So copies can be done asynchronous, can be overlapped with computation. Again, if we want to make sure that the certain copy has finished, one would have to synchronize the corresponding queue. Moving to testers, Magma provide testers for all the routines. These are also used as benchmarks to get the performance and compare with other libraries if available. So, for example, this is a testing for LU factorization in double precision. There are different parameters that one can give to those testers available with -h option. That's just one example, and Magma would print also the environment that is used. Like in this case was CUDA 6.0, 32-bit Magma integers and things like that. And then you would get the performance. In this case, we requested ScaLAPACK computation, meaning on the CPU we also computed what the CPU BLAS would give in this case, and that's MAGMA, and then some indicator of the error and a check if passes error checking. That's just an illustration that I already mentioned for the LU factorization on newer architectures. For BLAS, that's just one more example, in this case, symmetric matrix vector product. This, for example, can use atomics, and again, we can specify different options here. That's just putting the performance into a chart, again, comparing with other available libraries and CPU equivalents. One can test everything. There is a script, this Python script, runtest.py. So this will test all possible options, various sizes. Occasionally it may fail, but it's just up to arranging those tolerances in many cases. So these would run for a very long time, if more than 24 hours, if one would like to, for example, test everything. This is just one illustration of outputs of this run test and different options here to limit what is tested. And then at the end, it will give a summary of what has passed or failed. So moving to methodology, MAGMA is written in terms of BLAS. Higher level BLAS is preferred. For example, here, that's on older GPUs. You can see that the difference between DGEM and other level 2 BLAS like GEM-V is about 31 times, which automatically gives you that if you code a routine that is not reusing data, you would get less than 3% of the peak of these machines. And this ratio here increases. For A100, for example, is about 50 times. How the factorizations are done mostly are hybrid factorizations, as I mentioned. On the critical path, we will do panel by panel. When we do hybrid factorizations, the panel would be sent to the CPU to compute those critical factorizations as fast as possible, and then send them back to the GPU to do matrix updates. So these are matrix multiplications. When it's done correctly, one can overlap a lot of the work as shown on this tray. So this is what the GPU is doing. So as you can see, it's totally busy and also overlaps the work that the CPU would do on the panel. So as a result, you get the routine running as fast as you can run the gems on the GPU. Again, summary, when you do that, how this translates to performance on higher level routines. This is again the LU factorization. The same methodology can be done for two-sided factorizations. These are for eigensolvers. And now I will move to other functionalities, namely the batch routines in MAGMA. These are used in many applications, from machine learning to, as I already mentioned, the SEED co-design center. These are for high order finite element methods. So for batch computations, in many applications, you would have to do a sequence of routines that are small in size. And if this was a PowerPoint, you could see the animation, but these are PDF files, so we don't have animation. But basically, if you map them one by one on the GPU, you would not use efficiently the GPU. Many of the cores would not be used. So That's why we group them together into single batched routines, and we can map them then very efficiently, all illustrated here. Benefits could be very high, like 20 and more times speed up compared to if you pipeline your computation or even put it into different streams. So just knowing in the interface that we will do a batch of operations, there are a lot of acceleration that we can provide. And these are used in many places. Magma provides all these routines so far, LU, QR, and Cholesky, and solvers based on this, and matrix inversion, and all level 3 BLAS for fixed plus variable size, and many level 2 BLAS as needed, and auxiliary routines. We lead also efforts to standardize these efforts to have BLAS API, batched BLAS APIs. This is also with vendors and other people from the community. And these are more on the goals for that. This is just one illustration of how the APIs would look like for batch routines, including if it is variable size. So again, trying to follow the SLAPACK standards plus adding some pointers here and there when we want to deal with multiple matrices. And then we have performance numbers that show speed up on various architectures compared to different vendor libraries or other implementations. As I mentioned, Magma targets acceleration besides just providing those reference implementations. So that's for LU, for QR, acceleration is even more. Batch Cholesky. Magma is supported from the seed project, and this is basically to do various high-order finite element discretization and solvers, which result in various tensor contractions that can be done with batched computations. So some performance illustrations are shown here. Seed has various backends, and Magma provides one of the backends there. Of interest there are a lot of detail of how these are ported there, but main concern is also how to fuse kernels, because this sequence of batched operations there can also be done in a sequence to reduce communication. So we will fuse such sequences of different BLAS routines to get even higher performance speedups, as illustrated here. Other routines. I think I'm getting out of time, so I will try to wrap up actually. But Magma has also native routines for the factorizations. I mentioned hybrid. Hybrid sometimes are not faster just because the CPUs are getting slower, or the vendor libraries on the CPU may not be well optimized. Mixed precision, we already talked about this, very big speedups, just making sure we can use the lower precision calculations. Magma has a sparse component. Most of this is actually overtaken by the Ginkgo library that started as the Magma sparse, but we still support whatever is the most basic functionalities of different routines, preconditioners, kernels, and data formats. It is C style, so there are structures to describe, for example, the solvers and the matrix types. And when the matrix types and the solver are described in those structures with function calls, then there is Magma desolver, for example, just passing the pointers to the data and those structures describing the solvers that to be used, and the options, and then this would solve using iterative methods. Moving for 5 minutes for the FFT tutorial. We provide very fast multidimensional FFTs with different precisions, complex to complex, real to complex, complex to real transformations, also discrete cosine, discrete sine transform, and convolutions. We also added batched FFTs. This is the structure. So we of heFFTe, we depend on a lot of other vendor libraries when available. So we would use those, and we would use them as backends. So heFFTe has a lot of backends that often would use the 1D FFTs that vendor libraries provide and make those available for large-scale distributed systems. Support now is for all GPUs that are of interest for ECP, NVIDIA, AMD, and Intel GPUs. Latest release is 2.2. And we get very good scalability as illustrated here. This is the strong scalability, 90% of the roofline peak, meaning is just communication. If we ignore all the computations just to do the communications needed, we would get to 90% of this roofline peak. This is about the availability, where it is available. It's a Bitbucket repo. And support I already mentioned. The installation is similar to what we have in MAGMA, standard options to install. These are the different functionalities. So it is very flexible in terms of data supported, data format supported. This is more about the scalability on Summit, weak scaling. It's very good compared also to other libraries. heFFTe outperforms them significantly compared to theoretical peaks like roofline peaks, also very good. About how it is used, there are these steps. So one would describe the processor grid first in syntax like that. Then it will describe each process, what part of the computation are they working on, and what are they going to have at the output. So this is the data distribution. Intermediately, there are some options. So these can be also specified, or we can tune them if the user doesn't know. And then one would create a plan how the FFT would be computed like this. And then one would call the computational routines like that. Also, there are various tracing functionalities that one can trace and see the execution, exactly what happened. So that's one illustration of how we will call. There are various options all available and described. And then there would be a summary of the execution, including timing, what grids were used, what gigabyte per second was achieved, error, and things like that. For tracing, we can do our own in-house tracing like this, or use Vampire Trace, for example, as shown here. heFFTe, we help a number of applications to integrate heFFTe into their codes. And this is just one illustration of exactly what is happening there before and after. As I mentioned, originally the code running on CPUs, for example, may have half of the time in FFT. After that, actually half of the time in MPI communications. After acceleration, most of the code is actually MPI because all the computations get accelerated significantly. In this case, 42 times, for example, the kernels are accelerated using the heFFTe code. And that was the last slide. And I managed to finish with maybe 2 minutes. for questions. Oh, 4 minutes. Thank you. Yeah, if there are questions, I'd like to answer. Let me see.
We had one in the chat, but I think that's been answered already. It's just about magma sparse.
Okay. Oh yeah, the Ginkgo. Yes. So most up-to-date functionalities are in Ginkgo. Magma supports the one that were originally in Magma, and we port them to new architectures, but we haven't recently added new functionality there. I think I'll stop sharing. I think I had to rush some of the slides, yes, but they're all available. I think somebody already asked at the beginning, so we put them on the ECP site where all the slides are available.
Okay. All right, well, if there are no other questions, thank you all for coming. And if you are trying out SLATE or MAGMA or heFFTe and have any questions, feel free to reach out to us, and we will try to address your issues as as we can. Yeah, enjoy the rest of the ECP conference.
Thank you, everyone.